let's move on to the next speaker. The second speaker today is Ya-Hui Zhang. Ya-Hui is a postdoc from Harvard University, and he will tell us about electrodetection of spin liquids in double moiré layer. Ya-Hui, it's all yours.
So thanks for inviting me here for this wonderful workshop. So today I will talk about our recent work with Ya-Hui. So the title is electric detection of spin liquids in double moiré layers. Okay. So the basic idea for this talk is our propose a new kind of system, which we call moiré bilayers. So this proposal is based on two recent experimental progress. So the first one is the quantum Hall bilayer experiments. And the second one is the moiré surveillances, which we just heard from Van's beautiful talk. So I will propose a generalization of these two experiments to a new system, which I call double moiré layers. And I will show two features of this new system. So one feature is that if certain spin liquids can be realized in this new system, they can be easily detected. So we can have a smoking gun evidence for spin liquids in this new setup. And the second point is that I will show you some theoretical evidence that such spin liquids can actually exist in this system. Okay, so the proposal is largely inspired by the recent beautiful progress on the quantum Hall bilayer systems. So it's done by Corinne Dean and Philip King's group on the bilayer setup. But you can also find some previous literatures on the more conventional quantum Hall setup. So the basic idea is we have two layers. They are separated by an insulating layers. And this insulating layer will forbid tunneling between the top and the bottom layer. So the two layers can only be coupled through the Coulomb interaction. And the experiment is done at high magnetic field. So for each layer, you have a half field Landau level. And now we have two half field Landau level. They couple to each other through the Coulomb interaction. And in these beautiful experiments, they found a very, very clear evidence that the ground state for this bilayer system is actually an exciton condensation phase. So the most amazing part of the experiment is that in this experiment, they can actually measure the conductivity of the exciton. This is usually very hard because exciton is neutral, and you don't know how to measure the conductivity. But in this setup, people can do a counterflow transport. Basically, they can let the current move towards the right in the top layer, and let the current move towards the left in the bottom layer. And then if you think in terms of an exciton formed by one electron on the top layer and one hole on the bottom layer, then in this counterflow current, the exciton is actually moving together towards the right. So the counterflow current is actually a net current of exciton. And through this method, they can measure the conductivity of exciton. So they can measure the RV curve of the exciton transport. And from this RV curve, they can confirm precisely the prediction of the constant Leeds-Solis transition for the BEC state of exciton. So this is a really beautiful experiment. So the question I want to ask in this talk is the following. So can we move forward and realize some even more interesting phases than just the BEC state? So this is my main goal of this talk. And to do that, I wanted to give you a different interpretation of the same experiment. So in previous slide, I show you that we can understand it as an exciton condensation. But actually, the same setup can be also understood as a spin-or-half model. Basically, we can view the top layer as a spin-up and the bottom layer as a spin-down. This is just a redefinition. And in the experiment, the charge of the two layers are separately conserved. So you can do a linear combination and define two conserved quantum numbers. The first one, I will call it as Q, as the total charge. That's the total charge of the two layers. The second one, I will call it as SC, as the relative density of the two layers. So as the SC component of this spin-1/2 degree of freedom. And you have two global U1 symmetry. One corresponds to the conservation of Q. The other one corresponds to the conservation of SZ. So if you think it in terms of a spin-1/2 degree of freedom, you actually have an easy plane anisotropy. So you only have SZ conservation. However, in the small distance limit, the SU2 spin rotation can actually be recovered. So to see this, let's just round down a Hamiltonian. So for this system, it's just a Coulomb interaction. It have two pieces. So the first one is just the intralayer repulsion, U, and the second piece is the interlayer repulsion, U prime. Because there are a distance, so the U prime must be smaller than U. We can do some naive estimation. So the U will be roughly proportional to 1 over LB. LB is the magnetic length of the lambda level. And the U prime will be 1 over square root of LB squared plus D squared, because you have a distance, D. You can do some simple calculation and show that the difference between U and U prime is proportional to the D over LB squared. So the ratio D over LB will be very important in this bilayer setting up. And in the experiment, they can go to small d over LB limit because they can tune the distance to be as small as 1 nanometers. But the magnetic length is at the order of 10 nanometers, so 1 order of magnitude larger. But in this limit, you can find that the U prime is roughly equal to U. So interlayer and interlayer repulsion is basically equal. And you can rewrite the Hamiltonian in terms of Q and SZ. And you find the SZ piece is basically 0 in this limit. So you only have a repulsion between total charge. And the full Hamiltonian has a SU2 spin rotation symmetry in the layer space. So in this limit, you can really think of this system at a spin 1/2 lambda level. And the exciton condensation phase are just described. You can view it as a XY ferromagnetism. And I also show you in the previous slide, we can do some counterflow transport. And in this spin language, it corresponds to the measurement of a spin current. Because you let the top layer and bottom layer have opposite current. In the spin language, it means the spin up and the spin down are moving in opposite. That's basically the spin current. So in this setting up, people can actually measure the spin conductivity. So that's the main observation I made. Okay, we can make this mapping between spin and exciton more mathematically precise. So there is actually a very well-known mapping between a spin 1/2 degree freedom and a hardcore boson. But in this bilayer system, this mapping actually has a physical meaning. So basically, you can think of the system as a spin 1/2 degree freedom. The two layers can be labeled as spin up and spin down. You can also view it as an exciton degree of freedom. So here we can view so if you have one electron on the bottom layer, you can view it as the vacuum state of the exciton. And when you have an electron on the top layer, you can view it as we apply a creation operator of exciton on top of this vacuum. You can also map the operators between the spin and exciton language. Basically, the SZ operator will be mapped to the density of the exciton. And the S plus operator will be mapped to the creation operator of the exciton. And similarly, S minus operator will be mapped to the annihilation operator of exciton. So this is just a mathematical mapping. And in this mapping, the counterflow current corresponds to the spin current in the spin language and the exciton current in the exciton language. So right now, I didn't do anything. I just use a different language. But this actually is very useful because if you think in terms of exciton, then the exciton condensation phase is the most natural phase you can imagine. But if you think in terms of spin, we actually know many more interesting phases. So here in this previous experiment, we just realized XY ferromagnetism. Basically, SX is polarized. But we know in spin models, we have many more possibilities, such as near order or valence bond solid. But in this talk, I will focus on two other even more exotic spin liquid phases. So one is current spin liquid, the other one is spinor Fermi surface state. You can also map it to the exciton language. So the current spin liquid corresponds to a fraction quantum Hall state of exciton. And the spinor Fermi surface state corresponds to a bosonic metallic state of exciton. So the real goal of this talk, of our work, is to design a similar bilayer system to realize these more exotic phases. And to do that, as we all know, that to have a spin liquid, we need an anti-ferromagnetic correlation. So then we cannot use the quantum Hall bilayer, because in quantum Hall bilayer, in Landau level, you will find that the spin correlation is ferromagnetic. So you naturally only get the ferromagnetic state or exciton condensation phase. To realize spin liquids or more exotic exciton phases, we need anti-ferromagnetic coupling, and this can be realized in some lattice Hubbard mode. So we can generate J from T square over U, the super exchange term. So based on this observation, our proposed to generalize the quantum Hall bilayer setting up to a Hubbard bilayer setting up. So still, we want a bilayer separated by an insulating barrier. But for each layer, now we replace the Landau level with a Hubbard model or a triangular lattice. And for each layer, you have a larger Hubbard U, which is roughly proportional to 1 over AM. AM is the lattice constant within each layer. And we also have another term which is important. That's the U prime term. That's the interlayer repulsion on each side. So in this case, it will become smaller than U because you have a distance D. But as very similar to the quantum Hall bilayer setting up, if the distance D is smaller than the interlayer lattice constant AM, you will find that the difference between U and U prime is very small. So you can suppress this difference in the small distance limit. And if we are in the limit that D is equal to 0, you find that U prime is equal to U. And in this limit, we can really use the layer degree of freedom as another pseudo-spin degree of freedom, and we will recover a SU2 spin rotation in the layer space. So this is basically our proposal. And to realize this, apparently we need a very large lattice constant, because we want it to be much larger than the distance. So you cannot just put an ordinary Hubbard model. That does not work. So we really need a Hubbard model or a super lattice. And the good news is that we don't need to worry about it. It has already been realized. And we all hear from Fan's talk in the previous talk. So in the last 2 years, there are many experimental progress in the moiré super lattice. So the field is initiated by the magic angle twisted bilayography. But here our focus on 2 other systems. So in this system, we don't need to twist. So I think it's easier to generalize to the bilayer setting up. So one of the system is ABC trilayography aligned with HBN as done by van-der-Waals group. The other one is just a TMD heterobilayer we just heard from the last talk. So the idea is very simple. Basically, you put HBN on trilayography. You find that there is a lattice mismatch between the 2 lattices. Then HBN will provide a super lattice on top of the trilayography. And the trilayography will simulate a Hubbard model. And in these experiments, people already found multi-insulators and interfilling of this trilayography. Yes, in another word, so we already have a Hubbard model on moiré super lattice. And what we are going to do is just to have 2 such systems and put them together. And the idea is we can realize something which cannot be reached in single moiré. Okay, so this is some concrete setting up. So as I said, we can do it for graphene or TMD. So let me focus on the graphene HBN graphene case. So the other one for TMD is very similar. So if you look at the right figure here, we have 3 layers graphene, HBN graphene. So each graphene is an ABC trilayer graphene as done by van-der-Waals group. So if we just focus on the bottom 2 layers, HBN and graphene, then it's basically the experiment in van-der-Waals group. It has already been done, and people already found a multi-insulator and a Hubbard model for this graphene layer. What we do now is we add another graphene layer on top of HBN, but then this HBN can provide another super lattice on the top graphene layer. So both the top and the bottom graphene layer now have a moiré super lattice. So a crucial step is we want these 2 moiré super lattices to be aligned. So this is actually the most non-trivial step in this proposal. But as a theorist, I don't have any suggestion on how to do that. So I will just assume that someday our experimental colleagues will fabricate this system, which is not easy. But in the remaining talk, I will show you that some interesting effects can arise if this can be done. Okay. So if you look at the length scale, so we have So the D over AM is a very important parameter. So in this experiment, D will be decided by the HBN length. So I think you can make it as small as 1 nanometer. And the latest scale of the moiré superlattice constant is at the scale of 10 nanometers. So it's actually at the same order of the magnetic length in the quantum Hall bilayer setup. So this D over AM ratio can be roughly equal to the D over LB ratio in the quantum Hall bilayer setup. And so we can indeed go to the small d limit. And in this limit, we can really have a hybrid mode. So we will combine the layer as a pseudo spin, and we have a approximating SU2 rotation in this pseudo spin. But in this case, of course, for each layer, we also have some other flavor like spin and valley. So we will combine layer and spin and valley. So they form a large super spin. And then the low energy model is a hybrid model or triangular moiré superlattice. And for each electron, it has many flavors. For example, in graphene HBN graphene case, you will find that you have 4 flavors formed by spin, valley, and layer. For the TMD bilayers, you will have only 4 flavors because spin and valley are locked together now. So you only have a spin degree of freedom. And now you add a layer. So in total, you have 4 flavors. So it's kind of a SU4 hybrid mode. So of course, we also have some anisotropy. But so at the starting point, I will just ignore these small terms. And we want to analyze the SU4 or SU8 hybrid mode or triangular lattice. So in the remaining, I want to just tell you 2 things. So the first one is that if certain spin liquids are realized in this system, we can easily detect them. And the second is I will show you some evidence that they can exist. Okay, so let's do the first part first. We want to detect the spin liquids. We just assume they exist. For this purpose, I want to make a simplification. So I want to assume that we can polarize spin and valley. So for each graphene or TMD layer, we assume it's just spinless. And in this case, we only have 2 degrees of freedom coming from the layer. So the low energy model is just a spin 1/2 hybrid mode. And in this case, it's formed by top and bottom layer. So this model was also discussed in Fan's talk. But in that talk, it was formed by spin. But now it's formed by layers, pseudo spin. So the good advantage from this setup is that we can measure the spin current through counterflow transport. Okay, you can also think this. So we will focus on the half field case. So the total charge on both layers, when you sum the both layer charge together, is 1. And in the large U over T limit, we enter a multi-incident. So the charge is frozen. You only have a spin degree of freedom. This layer pseudo spin degree of freedom. And you can also map it to excite. It's just a different language. And this model has been well studied by many people. And this is a phase diagram shown by numerics. It also appeared in Fan's talk. So basically, in the small T over U limit, it's described by a Heterostructure model. And we know the spin formed a 120-degree new order. If you think in terms of exciton, it is actually a super solid. So it's like exciton condensates, but at a non-zero momentum. So the most amazing part is people found in the intermediate T over U, there is actually a spin liquid phase. So in the literature, there are actually 2 candidates for these spin liquid phases. So right now, we don't know which one is actually the true ground state. We're not trying to solve this problem. What I will tell you is that for these 2 candidates, we can have a very clear experimental signature, and then experiments can distinguish these 2 phases. So one candidate is a current spin liquid. The other one is a spin from surface. Okay, so yes, please.
Can I want to ask you a question about the setup in the moiré. Can you go back a slide?
This one?
There, yeah, thank you.
Yeah.
So does one have to arrange some relative alignment of the top and bottom layers in these tri-layers so that they have the same moiré potential? You know, if I, for example, translate one the upper layer relative to the bottom
Yeah.
layer
So
slightly, or
it's not
something like
easy.
that?
So you first need to have the equal twist angle, and second you need to make the shift also equal. So otherwise there is a shift.
Yeah.
Yeah.
Is that a generic situation that you have kind of shifted moiré potentials in the two layers? So
I think it's kind of random. It depends on the initial condition.
yeah.
So it's not easy to control. So
Okay, thanks.
yeah, but I think this is not the most optimized setup. So I think there may be some better ways to design a moiré bilayer. But anyway, this is just some theoretical design. It's not the best design. Okay. So we have two candidates. So one is the current spin liquid, one is spinor Fermi surface. So how do we detect them? So in this setup, it's very easy because we can measure the spin current. So if you have a current spin liquid, if you think in terms of exciton, it's actually a 1/2 Laufing state of exciton. So it's very similar to the electron version of the fraction quantum Hall state. So you have some anion with fractional statistics, and you also have a fraction quantized Hall connectivity, but it's in terms of exciton. So you cannot prove it use the usual charge transport. But the good news is in this bilayer setup, we can actually measure the conductivity of exciton through counterflow. So you just measure it, you should get a 1/2. And in this model, so the time reversal is actually spontaneously broken from this phase. So this phase is actually, you can view it as a fraction quantum anonymous Hall effect of exciton. So it's quite amazing phase. The other candidate is spinor Fermi surface. In terms of exciton, it's a bosonic metallic phase. So usually when you have a boson, it just condenses and form a superfluid. But when you have a strong interaction, like in this system, you will find that the boson wants to fractionalize or split to two fermions, and each of fermions just form a Fermi surface. So if you do counterflow transport for this exciton conductivity or spin conductivity, you should see some metallic behavior. Basically, the rho XX should be proportional to some power law of T. So I think it's also very easy to detect if it really exists. Okay, so in this slide, I just show you we can detect the spin liquids. So then can we really have them? So in this slide, I make a simplification. So I'll assume within each layer, there is a spinless electron. But in reality, within each layer, we also have a spin-less level. If you add it, you have a SU4 or SU8 hybrid mode. So this kind of model has not been well studied in the traditional condensed matter physics. We are just beginning to analyze it theoretically. So this is just some first analysis. So we just do some larger mean field theory based on Albrecht Fermi for more things later. I don't want to go to the technical details. So let me just provide two take-home message. The first is for SU8 model relevant to the graphene bilayer. So even at the integer filling wall, so even in the Heisenberg limit, you will find a current spin liquid. And for SU4 case, relevant to the TMD bilayer, at the integer filling 3, in the Heisenberg limit, you find it's a crystallized phase. But then you increase T value, you find in the intermediate regime, actually with a very small T value, you enter the current spin liquid phase. And these current spin liquid phase are kind of similar to the one I just described. So again, you can see anomalous Hall effect in counterflow transport. So if they exist, you can easily have a smoking gun evidence for them. Okay, so this is basically my talk. So in summary, I just propose a new kind of system, just combine two moiré layers from a bilayer system. I wanted to say that in this system, you can simulate some SU4 or SU8 hybrid model, and you can realize some spin liquid phases. But the most amazing thing is that you can have a smoking gun evidence very easily from counterflow transport. This is usually impossible in other setup of hybrid mode. So that's all. Thank you.
Thank you, Ya-Hui, for a great talk. So let's go into the Q&A. Okay, let me ask one question. So, when two layers are shifted by some vector, can you realize other type of superlattices?
Yeah, you can realize a different model, but I don't know how to analyze it. So that's a new question. Yeah, but at the starting point, I think we wanted them to be aligned.
Mm-hmm.
I guess maybe I can, another question kind of along these lines, but let's forget about the alignment. But the right-hand side picture with the graphene, I thought with graphene I'm supposed to not adopt these simple Hubbard model pictures and worry about, you know, band obstructions, etc. So where did that go in the graphene side?
Okay, so for the graphene, it's actually interesting. So in the graphene case, you have a displacement field, and when you tune the direction of the displacement field, you find on one side you have a topological band. So in that case, it's not a Hubbard mode. But when you reverse the displacement field D, you have a trivial band, and in that case, you can be the Hubbard mode.
So you're taking into account the asymmetry that's induced in the structure. Is it what's the microscopically? Am I supposed to think about? Should I be thinking about? Which vertical electric field should I be thinking about?
In this system, you can have many different vertical fields.
Yeah.
You can
which one do you
some
want?
gate on each layer. So by displacement field, I mean the vertical gate within each graphene. So because this graphene is not a monolayer graphene, it's a trilayer graphene. So you can define a voltage for each graphene. I mean, graphene has 3 layers, so there is a voltage difference between the top graphene and the bottom graphene layer.
I think I missed this. Sorry. So the top structure is already a trilayer?
Yeah, top structure is already a trilayer graphene. So we need to use a trilayer graphene.
Okay.
Yeah. And to get a multi-insulator, you need to apply a displacement field within this trilayer graphene. So then you can make the band flat.
Can you also go back to, I think it was maybe the second to last slide? If nobody's asking questions, I just want to see a bit about these results.
This one?
Look like, no, much later, where you talk. Yeah, I hit this one, I think. Yeah.
Okay. Sure.
So these are, what are we looking at here? What is the model?
Okay. So first, let me define the model. So the model is like a SU4 or SU8 Hubbard model.
Okay.
But we are going to go to the large U over T limit.
Okay.
And
so
you can
this is like a ring exchange and a Heisenberg.
Yes. So you can do a T over U expansion at each filling. And you find 2 terms. So the first term is just the Heisenberg term. I will call it J. But in this case, you find a 3-set ring exchange term K. So in spin 1/2, you don't have a 3-set ring exchange. But when SU1 for n is larger than 3, you have a 3-set ring exchange. So this is basically a calculation for phase diagram in terms of K over J. So K over J is roughly proportional to n times T over U. So I needed to rescale them with the n to do the larger calculation.
Yeah, and each of these is these are all insulators. So you're studying different representations of SU4 or SU8.
It's in all of the representations. So basically, you can define the total filling as nu t. So nu t is an integer. So nu t can be equal to 1, 2, 3, n minus 1. So this corresponds to different representations. But then you can define another filling nu. Nu is just the filling per flavor, so nu t over n. And at each nu, you can do a calculation. So basically in large N, so the phase diagram only depends on nu instead of nu t.
I see. Okay.
So that's the point.
Mhm.
So Ya-Hui,
Yeah.
Leon, are you done?
Yeah, I'm done. Go ahead. Yeah.
Okay.
Go ahead.
Yeah, so I just want to mention that we found some evidence, me, Anna, and Ella Tsenke found some evidence that just the SU4 Heisenberg model at filling 1, I believe, in this notation has a chance of realizing a spin-on Fermi surface.
Yeah, I know your paper, but I'm afraid I don't agree with your result.
Sorry?
So, I think I probably do not agree with your result because I also did some geometry calculation. But we can chat later.
I see. I see. Okay, that's about that. It's okay. And then also, I'm curious about the setup Leon was asking about this graphene, hexagonal boron nitride graphene. So have I just aligned everything? Then there is already a superlattice in the graphene given by the boron nitride, right? And then maybe I can make the boron nitride a little bit thicker so that the two graphene layers do not directly tunnel into each other. Then would it already be realizing what you want? Would that be possible? I mean, easier setup instead of having tri-layer and then a bunch of boron nitride and then tri-layer?
Can you say it again for this new setup?
Yeah. So I'm just imagining something simpler, as in for me, maybe each graphene is just a single sheet.
You mean a monolayer graphene?
Monolayer graphene, and then a hexagonal boron nitride, maybe several layers forming a crystal, assuming it's of this order, and then another sheet down the bottom. So the problem already gives a moiré structure, right? Because of the lattice.
Yes. Okay. So the comment is that for monolayer graphene HBN, you will have a superlattice. And this graph for monolayer graphene, you will also have some moiré band, but the bandwidth is very large. I think it's still at the order of 100 MeV. So I don't think you can realize multi-insulate.
I see. So
I think you really need ABC tri-layer graphene to do that.
I see. So the point is, you cannot make it
it's not flat enough.
I see. Thank you.
Yaroslav has a question.
Right. I have a question probably to the same point. I mean, in this structure, what is the role of boron nitride? Is it just an insulator? Could it be any other insulator, or is it important what is the orientation?
Okay, so the HBN is, so there is no electron in HBN. HBN is a strong insulator. So you don't need to worry about the electronic degree of freedom within HBN. So HBN plays two roles in this setup. So the first is that it provides an insulating barrier. So it forbids tunneling between the two graphene layers. This is the first role. The second role is I want HBN to provide the moiré superlattice for the graphene layers.
So the orientation then is important. If I rotate boron nitride, I will get something else.
Yes. So we want HBN and graphene to be aligned. So roughly at 0 twist angle.
Okay. Good. Thank you.
Hey, maybe I can make a comment about the large N calculation that Ya-Hui talked about. I mean, so there's a long history of doing these type of large N calculations for spin-a-half models where we know they're not that reliable. The advantage here, I think, I don't know if Ya-Hui mentioned, is N is really 8. It can be as large as 8. So the large N calculation is likely to be more accurate in this setting. So yeah, just a comment about the reliability of this approximation. Of course, eventually you should try to check it with other means like DMRG that there was some discussion about. But a priori, there's a little bit more hope that this phase diagram holds up. Yeah.
Just a question on the large N. I mean,
yes.
I remember there was work on this type of thing in in cold atoms, I don't know, Mike Hermele and a few others.
Yes.
Is there some overlap with that? What's different? I don't remember exactly what was done there, but I also
okay. I can give you a summary. So Mike Hermele found that so his calculation is done on square lattice, and he also found this current spin liquid, but his calculation is purely on the Hessenberg limit. So he found that when the filling is like 1/8, you just find a current spin liquid on Hessenberg limit. So we also reproduce this result on triangular lattice. So it agrees. So what is new is we add another term, this K term, ring exchange term. And in this case, we found, so for some other filling, like a one quantum filling, the Hessenberg limit is actually a placate out. But when you increase this ring exchange term, you enter a current spin liquid. So that's a new discovery.
Yeah, thank you.
I'm confused about something. Maybe you could correct me.
Sure.
So for the graphene case, is there a flux for the different flux for values?
Yes, there are different fluxes for the value. I'll just ignore it.
Okay.
Yeah.
Thank you. All right, so if there are no further questions, let us thank Ya-Hui again for his nice talk.